Dan Mayer, the celebrated math teacher from the USA, has often used surprise in his three-part videos as a way to get students hooked into a lesson, pique their curiosity, and get them asking questions. He once wrote about a slightly different way of using surprise. Mayer was at a state math conference giving a talk to teachers. He asked the group to give him three whole numbers between 1 and 6. They said 2, 3, and 5. Then he asked them all to evaluate those numbers in the expression x squared minus x. Do have a go yourself at the questions he posed to the teachers and notice any emotions as they arise. Most of the group began working on the task, but one teacher, he calls her Jan, sniggered and said, "I teach second grade." There was no way she was about to trouble her head to do that calculation. The group called out the results 2, 6, and 20. Did you get that? He then asked the teachers to evaluate those same three numbers, 2, 3, and 5, in this expression. Jan laughed openly, tossing her book to the side. The others carried on working diligently until someone said, "It's 0 for 2. Mayer responded with, "Oh, really? Strange. What about for 3? And in a few minutes, someone else said, "It's 0 for 3 too." Mayer expressed further shock and said, "Anyone got it for 5? When that turned out to be 0 as well, Mayer carried on his pretense of being surprised. He knew it would always be 0. And that was when he noticed Jan. She had straightened up in her chair, picked up the notebook that she had flung away, and begun to try and figure out what was going on. In the blog where Mayer recounts this incident, there followed a very interesting conversation between Mayer and his blog readers about what might have happened with Jan. She was totally unmotivated to do a task that had no purpose, a seemingly mindless calculation. But what got her attention, what seemed to give her a purpose, was the surprising results. The strange turn of events, of getting 0 for each number, made her eager to figure out what was going on. This is one of the ways surprise can act as a motivator. Many times I have heard people say that math needs to be made relevant to students' everyday lives, that is the only way to motivate them. While I agree it is truly wonderful for students to learn real-life math, math is essentially an abstract subject. What is really important for motivation is purpose. And purpose can be about real-life math. It can also be a useful bit of math that will help the math of the students they will learn in the future. Or it can be a surprising outcome that intrigues students to try and work out what is happening. There was nothing real life or useful for everyday life in the calculation Jan dismissed. But the surprising outcome gave her a purpose to figure out what was happening mathematically and do some math. Surprise is related to a crucial learning process called cognitive conflict. The notion of cognitive conflict was formulated by the influential developmental psychologist Jean Piaget in the early 20th century. Piaget's ideas have their roots in an evolutionary biological metaphor. In evolutionary biology, the organism adapts to its environment in order to survive. In Piaget's metaphor, the learner constructs personal theories and adapts these through assimilation and accommodation in order to reconcile their observation with their experience. Assimilation refers to the absorption of new ideas. Accommodation refers to the modifications that the learner then makes in order to fit new ideas into their pre-existing conceptual framework. Let's see if we can break this theory down a bit. When students experience a new situation, they compare it with experiences they have had in the past. Let's think of an early example experience of students in math that the greater the number of digits, the bigger the number. So 4,578 is bigger than 902, and it has more digits. These past experiences prompt expectations of what might happen in a new mathematical situation. In this example, a new situation might be when they meet decimals. If the outcomes are the same as the expectations they had, everything assimilates comfortably. So, when ordering decimals, 2.341 is bigger than, say, 1.23 and has more digits. All good so far, all fitting their expectations. But on some occasions, there might be inconsistencies and contradictions. 0.475 is smaller than 1.3 despite having more digits. This causes a perturbation or cognitive conflict. When this happens, it may produce an emotional response of disappointment, surprise, or even anxiety. And it also produces a basic and powerful human motivation in students to reduce this disequilibration. In their quest to do so, and with a teacher who cultivates and supports this cognitive conflict, as opposed to dismissing or immediately correcting it, students might revisit and review their experiences to analyze the cause of these inconsistencies. They might relook at the experience in a new way, and there is a change in the recognition pattern. This in itself is an act of learning and accommodating results. In our decimal example, students will relook at what makes a number bigger. A teacher could use this as a crucial learning moment of the fundamental understanding of place value. Piaget used the term equilibration to mean the elimination of perturbations. Cognitive development is characterized by expanding equilibration, by which Piaget means an increase in the range of perturbations that the learner is able to eliminate. Or in really simple terms, more surprises mean more learning. During the 1980s, math educationalists and task designers, Alan Bell, Malcolm Swan, and others in the UK, designed sequences of classroom tasks which followed a diagnostic teaching pedagogy for mathematics that also contained cognitive conflict. They compared the teaching of these tasks with teaching that was more explanatory in nature. They found that when misconceptions were explicitly addressed during teaching, achievement and long-term retention improved. But how these misconceptions were addressed was important. They looked at when conflict was avoided in teaching by, for example, giving explanations before students reached the conflict. They found that the tasks were less effective when used in that way than when teachers began with problems that exposed existing ways of thinking and students experienced cognitive conflict, then facilitated small groups and whole class discussions to resolve the conflicts that had come out. The study also looked at discussions within groups, and they found the resolution of cognitive conflict through discussion was central to this approach. For example, if a teacher set up a task to ask which is bigger, 47 multiplied by 3 or 47 add 3, students might quickly say the first one. When pushed for a reason, there might emerge the often believed statement, multiplication makes things bigger. When students are then given a series of multiplications, including some like 47 multiplied by 0.3 or 47 multiplied by 2/3, they will experience a surprising result. The answer is smaller. Here is the cognitive conflict, and therefore a point of attention and learning. This is a misconception that often comes up naturally in math classrooms. Teachers often correct it by simply telling, but it is a golden opportunity for learning. The surprise will have students' brain ready to learn a bigger idea. Swan and others say that at this point, group and class discussions are the best way to resolve these conflicts, rather than just telling students what to think. Another math teacher, Colin Foster, also an educational researcher, proposed an idea of mathematical etudes. As a teacher, he tried to have interesting and meaningful math lessons, but sometimes felt a bit of a fraud. When he asked his students to practice a technique or skill, such as multiplication facts or the division algorithm, he felt he was letting them down. He knew it was important to practice certain math techniques for fluency in order to be able to move on to higher order thinking, but it was so dull. The exercises he gave students were the opposite of the experience he wanted them to have in math class: wonder and delight. That's when he started paying attention to certain types of tasks that got students repeatedly practicing a particular skill, but also had hidden the within the bigger structure some nugget of a surprise that would captivate them. He began designing some of his own, and he coined a term for them: mathematical etudes. If you have ever learned a musical instrument, this term etude might be familiar to you. It is a musical composition designed to practice a particular musical technique or skill. But the compositions themselves are enjoyable and beautiful in their own right. Their purpose is twofold: to practice and to enchant. Foster used this term for the mathematical tasks he designed or collected that also had this dual purpose: to practice and enchant in math. And sometimes the enchantment was a surprise. There are many examples on his webpage, in the activities section of this course, and online. The Enrich website has many tasks that can work as etudes, as does Foster's own website. The task I described in the previous lesson, called 1089, can be used as an etude to practice three-digit addition. I have included tasks in the activity section of this course that are etudes. Do look at the one on hiccup numbers. It's my favourite. Mathematical etudes are a wonderful idea as a counter to those inevitable boring lessons of endless practice. It makes the conflict between teaching for wonder and teaching for fluency and technique irrelevant. You can do both at the same time. Finally, let's look at the work of Nina Movshovitz-Harder from the 1980s in her wonderful paper, School Mathematics Theorems, an Endless Source of Surprise. In it, she proposes that all theorems that are taught in school contain an inbuilt surprise. If teachers exploited these surprises, she says, students would experience math as an exciting, intellectual enterprise. She says, intellectual surprise usually gives us a sense of fulfillment and appreciation of some wisdom, a joy from its witness, and a drive to find some more. Making mathematical findings appear unexpected or even counter-expected is the secret to teaching mathematics the surprise way. She emphasizes that this way of teaching and learning is not an end to itself, but a way to intrigue students and gain their interest so that they can be open and excited to learn. Her paper is fascinating and full of interesting examples. Let's just look at one small example here. Consider the theorem: the angles in a triangle add to 180 degrees. This is a theorem that is considered very basic and is usually simply told to students, who are then given a set of exercises in which to apply it. It might seem a very obvious fact to those of us who have had a high school math education, but consider the child who has not yet heard it. It is not at all obvious. To reach the surprise potential of a theorem, it is usually helpful to assume we do not know it. So, this state of being, before children know this fact, can be used while introducing this theorem. Movshovitz-Harder suggests giving students a task of finding the largest sum of the interior angles from an assortment of triangles. When faced with all sorts of triangles of various shapes and sizes, equilateral, isosceles, scalene, acute angle, right angle, obtuse, very large, very small, very narrow, very wide, etc., children will naturally assume the angles are going to add up to different amounts. As a teacher, you can be pretending to assume the same too by giving them this task to measure the angles in each triangle and find one that is bigger than the rest. Imagine the surprise and befuddlement when all the angles for every triangle add up to the same number, 180. What a thing to discover by oneself. By the way, this task is also an etude if you wanted students to practice measuring angles. The contradiction of their expectations will cause students to be amazed at this discovery. You could go further and ask students to try and make a triangle which doesn't add to 180. By really engaging with the untruthfulness of the theorem first, like adventurers on a journey of discovery, students will be delighted and appreciate the truthfulness of it. I hope you have enjoyed exploring the critical and delightful role of surprise in mathematics and consequently in math teaching and learning. You have learned about what happens in the brain that promotes learning when it is surprised. You have heard what mathematicians have said about surprise and beauty in mathematics. You've done some math yourself with surprising moments hidden within it. And you've learned some ways of bringing surprise into your own classroom. Perhaps most importantly, you have seen how surprise can help a person change their self-belief about themselves and who they are, boosting their self-confidence and belief in their capabilities. Through all the intellectual wonderment that surprise creates, it also creates delight. Delight in learning, in math, and in yourself. Surprise really does benefit your well-being and that of your students by adding inquiry, joy, and a good dose of mathematical identity building as learners figure out patterns and surprises. So, a fitting way to say farewell at the end of this course, I think, is to say, I wish you lots of surprise in your round glass and teaching journey.